Здравствуйте.
По-видимому, нужно было дождаться, когда у нас включат в независимом университете трансляцию, потому что это не я, к сожалению, являюсь организатором.
Угу.
Вот я в
Хорошо.
следующий
Меня
раз...
слышно?
Да, вас слышно хорошо. Так,
Хорошо.
значит, давайте попробуем поделиться своим экраном. Попробуйте.
Да, сейчас. Только я вижу имена. Вы мне скажите, доклад на каком языке это нужен?
Сложный вопрос. Значит, я подозреваю, что Джинху говорит по-китайски, по-английски, и Суша говорит немножко по-русски. Я не знаю, насколько...
Меня не предупредили, потому что на английском. Нет, для меня это не проблема,
Нет,
как бы просто.
Нет, давайте вот что.
Да.
Делайте его по-русски. И у вас слайды по-английски или по-русски?
Не, смотрите, значит, у меня слайды по-русски, но я могу по-английски, это не проблема вообще, не капелька, просто я не слайды, а на
Ну,
планшете буду писать.
вы будете писать на планшете.
Не, ну я могу, в смысле, я сейчас могу подключиться с планшета и писать на планшете.
Короче,
Без
как вам
слайдов.
удобнее. Короче, тут в данном случае как вам удобнее. Тут никто не
Сейчас.
будет писать ни против русского, ни против английского, я думаю.
Хорошо, сейчас. Сейчас я подключусь с планшетом.
Так, вы готовы? Или еще не подключили
Сейчас, нет,
планшет?
еще пару минут сейчас. Или
Хорошо.
полминуты сейчас.
Мгм. Вы теперь едины в двух лицах.
Да, сейчас я
Игорь
подключу.
Бастер.
Мгм.
Здравствуйте.
Здравствуй, Саша. Вот как раз тут удалось подключить как раз сейчас видео, потому что некоторое время пришлось подождать. Ну ничего.
Ну
Надеюсь,
прекрасно. Еще как раз у меня тоже на самом деле возникли стандартные проблемы тут с VPN. Когда я
удивительно.
пришел,
Вообще
все
это
забыл.
очень начинается на любителя, потому что в некоторых случаях VPN не сам нужен, чтобы подключить Zoom, в некоторых нет.
Но вот у меня никогда, мне никогда еще здесь не удавалось подключить Zoom без VPN. А когда я почему-то перемещаюсь из помещения в помещение, иногда бывает ситуация, когда у меня вылетает вообще из системы компьютер, мне приходится заново логиниться, а иногда случается глюк, и вообще не хочешь ничего работать, интернет не хочет работать. И вот ровно сегодня это и произошло. Я сейчас опять перезагружал все заново.
Так,
Да,
здравствуйте.
как видно.
Так, все видно, да? Вот я
Да,
чиркаю.
вас видно хорошо.
Супер.
Все хорошо видно. Давайте, значит, решайте, на каком языке будете говорить, какой вам больше
Ну, на
удобен.
английском, видимо, да, раз уж
Давайте на
такое
английском.
дело. Так.
Ну, сейчас, да, сейчас тут у нас два иностранца.
И Иисуса
Не,
формально,
ну если бы я как бы... Да.
Иисусе формально будет, Иисусе даже будет формально защищаться по-русски. Ну, конечно, да.
Ну,
Но тем не менее, мне кажется, лучше поговорить по-английски там.
ну да,
Не, ну если бы я
дадим.
знал, да, я бы слайды на английском сделал. Ну, ладно.
Не
Ну,
переживайте.
ну
Да,
ладно,
все
ладно.
равно. Все, в принципе, я более-менее готов, да.
Давайте.
So, okay. So my talk is algebraic drum cohomology of soft function algebras. I will explain what soft function algebra means a bit later. So the idea is as follows. So in topology, there is a theorem due to Gelfand and Kolmogorov. And it says that a compact Hausdorff space can be constructed or how to say can be obtained. Space X can be obtained from our algebra of continuous functions on the space. So the algebra of continuous functions determines the space itself. So there's an analogous statement for smooth manifolds. So the same for smooth manifolds, and algebras of smooth functions. A good reference is Jetness.
Whose theorem is that for smooth?
It's probably Jetness-Struve, but it is written as Jetness-Struve in the book. But the theorem is probably older. But yeah, it's written
Well, I think
Jetness-Struve.
the first reference I heard about this was a reference to some papers by Alan Kohn.
Oh yeah, probably yeah. It's a known result, I think, before Jetness-Struve, probably. So, so in a sense, we can view topological spaces in terms of continuous functions, and smooth manifolds as algebras of smooth functions on these manifolds.
But in order to restore it, you really need not just the algebraic structure. You in fact need topological structure in the first case and the smooth structure on the second case, don't you?
No. Just from the algebra itself.
No, but how do you restore the topology then?
As a topology in which all of these functions are continuous.
Well, there are. I really don't think it's.
No. I think you're going to restore just from ring structure of CX.
Well, as far as ring structure is concerned, I think it's. I really have doubts, but. Well, I believe that one needs to take care of Sistar's algebra structure here introduce to restore the topology, but maybe it's easier, but I'm not sure. And the second case, you also need something else, a smooth structure. Otherwise, how do you prove that you restore a smooth manifold?
The proof itself, I don't remember, to be honest, but
No, it's easy to restore them as a set X.
yes.
Just a
So
set
the
of all-
topology.
Just a set of all maximal ideals there in CX. A set,
Yeah, and
set of
topology is the one in which all of these functions are continuous.
well, for instance,
It's the minimal topology.
For instance, discrete. Well, if you take discrete topology,
no, it's not minimal. No, it's not minimal. The minimal topology.
Oh, it's really something very abstract. I thought that C-style algebraic structure is really important here. It's part of Gelfand-Naimark theorem. But maybe in the commutative case, you can do some simpler construction. Not sure about this. Okay, let's go on.
Okay. So now the question is, if you have the algebra of smooth functions, can we in some sense restore from the algebra itself, restore kind of the differential forms on the manifold M directly? So the question comes from the following observation. So if you have a algebraic variety, let X be.
Yeah, sorry, I missed because of a poor connection. The explanation about the topology, about the smooth structure of M.
Well, the explanation was pretty abstract. The topology is the minimal, the weakest topology in which all the functions from CX are continuous. That's something too abstract, in my opinion. I cannot.
No, I mean, you asked about the smooth structure, and then I lost
smooth
my
structure,
connection.
yeah, and as far nothing was said about the smooth structure.
Yeah, I didn't prove and explain why, so it's kind of.
You didn't say anything about the smooth structure either, so
yeah,
you can just trust you.
So here, if you have X be an algebraic variety, then let's say with the algebra of regular functions A, then we can define differential forms, and the differential one forms are the associated sheaf to a module, to an A module. We call it like this: omega 1A, defined as follows. So I'll define the module, but the idea is you have an algebra, and if you want differential forms on differential forms on X.
So you mean a fine algebraic variety?
Affine. Yeah, sorry. Yeah, of course, affine. Algebraic, affine variable. Yeah. Affine. Yeah. So the module is defined as follows. So it's a module generated by the symbols dA. Those are formal symbols for each element of the algebra A. Modular the relations. So first of all, A is a K algebra, and D of any constant should be 0. Second, D over sum minus dA minus dB is also 0. And just write like this. And there should be a Leibniz relation that looks like this.
Is it a symmetric module, bimodule? So it's symmetric, right?
Everything.
I think in that case, you don't. In that case,
commutative.
the condition on scalars is redundant. Oh, I mean, of course, unless you
No.
don't you?
You
Don't
know
assume
that
the
D1
reaction of is equal to D1 squared, so it's equal to 2 D1s, but that's
Yeah, we know that D1 is 0. Why is
The
DC
field-
is 0?
The ground field is of characteristic 0, right?
Yep.
yeah. Okay.
You have to be able to kind of
Don't you assume that actually it's K-linear? Oh, you don't say
well,
K-linear.
yeah. If it's K-linear, then these two conditions are not needed. But the problem is K-linear, those are formal symbols, so it's kind of not too precise. So yeah, so
Right.
here I actually say it's K-linear. So no, sorry, I forgot. So D CA is C DA, or C is from the field. Yeah.
But doesn't it follow from the previous?
It follows. It follows from the another axioms.
Okay, it doesn't
from the first one, the second one. Yeah.
We don't care about the minimal set of axioms in any case.
Okay. So those are called Kähler differentials. Differentials. So from the Kähler differentials, you can construct Kähler forms. So like this is just exterior algebra over A of omega 1. And here you actually have a differential. There is a differential. Omega n plus 1 A. That looks like this. So D of F dg1, dg2, and so on dgn goes to df wedge dg1 wedge and so on times dgn, like this. So from here we immediately see that d squared is 0. And from the Leibniz condition, we know that omega bullet is actually a DG algebra. DG algebra.
Do you want to say commutative DG algebra?
Commutative, yeah, of course. A commutative.
Graded commutative DG.
Well, it's DG, so it's graded, but a commutative. commutative DJ. Okay. So we call it algebra of de Rham forms or Keller forms. De Rham forms or Keller forms. And so for an algebraic variety, affine algebraic variety, so F affine algebraic, and A example, A algebra of regular functions, we have actual differential forms is just the same as this algebra. This
Well, it
DJ algebra.
depends on what you call actual forms. Define the left-hand side.
Well, yeah. So this is tautology in my case. This is tautology. But in general case, you can define the left-hand side differently, just as a exterior algebra of this thing and this thing as a regular sections of cotangent bundle. And the definition was still agree. Is shown, for example, in Igorevich, in the book of Igorevich. So, okay. So now, if you want to take this definition and just say, let's say, let's take M a smooth for manifold, a smooth manifold, and say we consider this DJ algebra. So this definition works for any algebra, for any commutative algebra. This one. A is any commutative algebra, any commutative associative algebra. With identity, of course. So here we can just take the algebra of smooth functions and define this algebra. And ask, is it isomorphic? Is it isomorphic to just the DJ algebra of smooth differential forms on the manifold time? So the answer is, of course, no. In fact, this module is huge. So the result of Francisco Gomez, it's the 90s, I think 1990, is that if the dimension of M is at least 1, then the module, the C infinity M module omega 1 is uncountably generated. So yeah, in fact, you can just take a form. Let's say, for example, it's not an example of the theorem. So let me phrase it like so a lot of identities that you expect for differential forms are not satisfied in this DJ algebra. So we have in omega 1 C infinity m, example d of exponent is not exponent dt. But it's of course true in, let's say, for example, R.
I believe that's because you cannot actually express E of t as a finite formula of t.
Yeah, as an algebraic function. So the actual result is the so you have df t equals f prime t dt if and only if f is an algebraic function. Algebraic function. And so, yeah, so this module is very big, and the DJ algebra is, of course, also very big. So, but not all hope is lost. So the next thing we can ask is, how do cohomology groups behave? The homology groups of this DJ algebra. Well, not too good as well, but not as bad also. So let me explain. So the bad results, So let's say, for example, let M be just the real line, and consider the first cohomology of omega bullet for R. So this one is not 0. It was first proved in 1967 by Howard Osborne. And he just constructed closed, not exact form. So the form dt over 1 plus t squared is closed, but not exact.
So what happens in the usual smooth case? It is definitely closed and should be smooth. Should be.
But if it's exact, then
why is it exact in this case?
Well, if it's exact, then its antiderivative should be arctangents, right?
Yeah.
But again, the problem is arctangents and 1 over arctan and 1 over 1 plus t squared are not algebraically dependent. That's the main problem.
So actually, any function which has rational or polynomial derivative, but which is not polynomial,
which is not itself,
would do,
the same
right?
Problem. So the proof is not too elementary, but still, any function will do. So the good result, the first good result, is that the zero cohomology group coincides with the zero cohomology of M with real coefficients. It's not too elementary as well. Well, this one is, but okay, this one is easy. And why, I will explain in a second. So what happens in higher dimensions or for any other what we will call functional algebras was absolutely unknown. So in order to understand what happens, I have to kind of connect the DJ algebra for the algebra of smooth functions and the DJ algebra of differential forms on M. So that's quite easy to do, actually. So let's take the DJ algebra smooth functions, and I claim there's a map to just differential forms, smooth differential forms. We would call it pi, and it's very simple. So any form here is just the sum of forms that look like this. So we send it in a form that looks like this. And that's it. That's the map. So you can view this DJ algebra as just a way to kind of write a differential form as a formula. And here we actually say that you take a formula and you look at it as a differential form, smooth differential form. So that's a map of, that's a morphism of DJ algebras. And so we can ask, for example, is it a quasi-isomorphism? Is pi quasi-isomorphism? Well, we know it. The answer is no, because for example, in the case where M is just real line, we know that the left-hand side has the first cohomology not zero, right-hand side has cohomology 0. So that's a bad result, but it's not too bad. So let me explain why. So first of all, we know that theorem due to the RAM. So for smooth forms, there's a map of cochain complexes from smooth differential forms to smooth singular cochains. And this map, we just take a form and send it into a cochain that looks like this. And the theorem of the RAM is that this map is a quasi-isomorphism. So if we connect the map pi and this map, and what we have is this.
You mean compose, right?
Compose, yeah. If we compose the map pi and this map, Then on cohomology, we also have a map. Well, this is a map of complexes, of course. Well, it's quite isomorphic, so have a map to singular cohomology of M. Singular smooth singular.
Now, I believe in
cohomology.
case of smooth manifolds, there is no difference between just singular.
Here,
Singular.
because I write smooth, I just say
Okay.
kind of, so there's no confusion. So what was known about this map? Well, actually something was known. So again, Gomez proved that this map is surjective in even degrees. So if star is even, then this is surjective. And in order to prove it, he constructed, for any element on the right, he actually constructed an element on the left. But his proof doesn't work for odd degrees. So the first result of mine is 20 is this. So there is a map lambda from the singular cohomology with coefficients in R to the cohomology of this DG algebra such that to go here, then this composition is the identity map. So this one is lambda. So in some sense, so this is a canonical map. So it doesn't depend on anything. So in some sense, we prove that up to cohomology, for any smooth differential form, you can actually write a canonical formula, kind of. Well, it's not true, but up to a cohomology. So as an immediate, as a corollary, we have a canonical decomposition of the cohomology this algebra as a cohomology of M plus something.
So how do you construct this map lambda? Can you just sketch it?
So the idea is as follows. So on the smooth manifold M, we have a sheaf. Well, let's go step by step. So for M, we can define a pre-sheaf, pre-sheaves, find pre-sheaves, omega and C infinity. Let's with a wave because tilde, because it's not a sheaf, and it looks like this. So for on an open set, it's just the Keller differential forms on the open set U.
So why isn't it a sheaf on the nose?
Because
you can actually
I think the
extend.
gluing, yeah, the gluings are kind of bad.
Why is it bad? It's good. I don't see. It's actually, after all, it's flabby sheaf. C infinity is flabby, so there is no need to worry. You can actually use partition affinity.
Right. So I did this proof kind of long way. So the problem,
maybe the models are too big. That's the reason.
No, the shiftification is still too big. So
I mean the previous remark.
I think I believe that there is, you can just use partition affinity to glue everything. If you have.
Well, this one is a soft.
Yeah. Okay. Continue.
Right.
So this one is a soft sheaf, right? The C infinity. So those are. So those are, if we shiftify, then those are smooth, soft shifts. Why this one is not a shift? Yeah, good question. I don't.
So if you have a series, I believe that the condition of that the sheaf is that when you have a series of an open cover and you have an element on every, and have some element, a section at every element of the open cover, which match on the overlappings on the intersection. Yeah. Then you have a unique map on the set. But
you cut out. I think.
But maybe uniqueness doesn't work. That's what I would say. Maybe uniqueness doesn't work.
Okay, sorry.
Yeah, that's
so
probably
we have to be able to glue sections from pre-sheaf, and then it'll be a sheaf, right? So yeah, I'll think about it.
No, I mean, if you have just the form of the form which you can write down as a F0 wedge df1 wedge and so on, wedge dfn, right? You actually are supposed to find the global sections, global functions f0 and fn for fn.
The problem was probably is that these models are not finitely generated. Because
no, of course not. No.
You cannot just. It's possible you cannot find global functions in this case.
Yes,
I mean,
yes.
And I don't think that the finite functions is actually important.
Yeah, the reason probably is that it's not a smooth manifold. The model is bigger than just forms on them smooth manifolds. So the geometric intuition work.
Yeah, I mean, if you have fi dgi and you have such elements on every open set, and you try to glue them, you need to separately extend fi's and separately extend gi's, which can be quite.
Yeah, that's the problem. Yeah. So the problem. So the problem. So if you take section on this, and we can on the whole manifold. action on this open set and continue on. So the continuations are different, even if this one is
that's
coincides. Yeah,
uniqueness.
and that's the big problem. Yeah. Exactly. So we have to shift apart. So from this one, we can like a shift is just the pre-shift shift part. So shiftification. So it actually is so the differential stays and we have a complex of shifts. Like this on M. On M. So now what we can do is we can look at the constant shift on M. So let Rm be the constant. It's a constant shift on M. So by Rm0, we denote the complex like this: Rm, 0, 0, and so on. So this one in degree 0. This is degree 1, and so on. So there is an actual, the obvious map from this constant to our shiftification.
Just the inclusion of scalars. Okay.
Yeah, just the inclusion of scalars. Including. And so now we can, this is a map of complexes. And what we can do is look at the hypercohomology. Hypercohomology of M of course Rm0 to this hypercohomology. M with coefficients in. So this one is isomorphic to just simple homology of M. Well known. But now this one is actually isomorphic. The homology of this one. This one is not trivial.
So it's because this shift is actually, how do you call this, flabby, that you can restore.
Soft. Yeah.
I mean soft, yeah. When you, so it's in double complex, the spectral sequence collapses at the first.
Yes, but you still need the fact that the global sections, so we still, so the lemma, the most important lemma here is that so you have this sheaf and the sections. So the global sections whole manifold are actually just the algebraic Keller forms. So it's not true for open sets, but for the whole manifold, it is true.
So how do you prove this?
So this one is quite
Open
technical.
set, it was for open set, we concluded that we need to simplify because we don't have the gluing property, but here you still...
Yes, for closed, you don't need the gluing property, but it's quite a technical proof.
What do you use?
Wait, let me...
Not details, that how do you prove this, just can you sketch it?
Yeah, I have to... I don't really remember, I have to look it up real quick. Yeah, so so the proof yeah, so we take a form. So for injectivity.
So there is a map in one direction, from left to right, from right to left, sorry. In one direction,
From right to left. Yeah. There is this map.
So how
From
do you define...
those are global sections of pre-sheaf. Those are global sections of a sheaf.
Yeah.
So we have to prove that this one is injective and surjective. So if we take a form here, let's say it maps to 0. Well, what does it mean it maps to 0 here? It means that there's an open cover such that the restrictions of omega to M is 0. So say there is open cover UI such that omega equals 0 in let me write like this. Okay. The restriction of omega on UI is 0. Now let's take division of unity.
Partition of unity. What?
Partition, yeah, sorry. Partition of unity. Phi I. And now what we want is just take what we want. We want to take omega and say that it equals phi omega. And then say that the restrictions are 0, so the whole omega is 0. Now the problem is for this one you need another lambda. So if you have an open set U in X and have a form open form omega in omega C G U, and omega restriction U is 0,
I think then you have omega in omega C infinity of M.
Sorry, yeah, so M. Now, say from the infinity of M such that support of phi is in U. Then phi omega is 0. Is 0 as an element of omega n. So this is the most non-trivial kind of part in any of this. Everything else, just if you have kind of this result, then everything else follows. So the idea is this. So the idea, sketch of this one. So we know that the support of phi is a closed set. So we have from M to F, C infinity F, this one is a surjection because C infinity is a soft shift. Okay. Now, also omega n C infinity M to omega n C infinity F is also a surjection for the same reasons.
Yeah, for the same reason.
Yeah. Now, what's the kernel of this map? So the kernel, I call this map res from M to F. So the kernel of res is generated. Let me write here not n, but just bullet. It would be simpler to kind of formulate what I want to say. So what do I want to say? Oh yeah, so this one, so let's distinguish this map and this map. So let's call this map so res, but this one res bullet. So we don't confuse them. Now, my chart. So this kernel is generated by the kernel of res and the D of this kernel.
Generated in the sense of module of what?
No, as an
algebra?
ideal of a DJ algebra. As an ideal of a DJ algebra.
Okay.
So now what we actually have to do is just to prove the results for proof for the forms omega that looks like this: dt times lambda plus u eta, where t
Prove what?
and u.
We have to prove what? I said we have to prove, but we have to prove what?
That phi times omega is 0.
Okay.
So phi times omega is 0. This one. And eta and lambda are forms, algebraic forms. And so this one is proved just by writing the formula. So we write phi omega, say that it's phi dt wedge lambda plus phi u eta. Now this function is just 0. Sorry, here assume that the restriction of u is 0. So phi times u is 0 because there's just functions with non-intersecting support. But now here, so this one is 0. Yeah, so here phi times dt is d t times phi minus t d phi, and this one t seconds. Yeah, sorry, it's quite technical, so I have to kind of
I think you need to assume that phi is constant, scalar constant.
no, phi is just a function. So here, the restriction of u and the restriction of t should be both 0. So let me highlight it. So phi, so again, so phi dt times, oh yeah, so I remember. Okay. So in case of the something being constant, yeah, you're right. So we know there is a function g, smooth one, such that so first of all, the restriction of g to f is 0, and the restriction of g to support of t is 1.
So what is f?
F is the support of
Phi.
support of phi, yeah. Mhm. And so here we know that tg is just t, so write like this, because g is 1 on the support of t. But now we can open it by the Leibniz rule, the phi g dt plus phi t dg. Okay, but now this one is 0, and this one is 0 as functions. So this one is 0. So actually phi times dt is 0. So this sound is 0.
We assume about t that its support is what?
The support of what? Of t?
On m is equal to 0, right?
The support on f. So the restriction of t on f is 0. So if we restrict t on f, it's 0.
Mm-hmm.
Yeah.
And g is also 0.
So we have just two closed sets,
so,
and g is just 1 here and 0 here.
So the support of t does not intersect the support of phi. And
Yeah.
that's problem.
Yes. So that's the lemma. And now from this lemma follows. The injectivity follows.
Mm-hmm.
Now for surjectivity, again, it's kind of a technical result. You have to prove it. So for surjectivity, we prove on each stock, on stocks.
Okay, and that's more or less
so we construct
standard thing, right?
Yeah. So we can construct the pre-image, but now the idea is why this pre-image is what we need. So and that one we check on stocks. So yeah, so this result that the sections on closed sets coincide is not trivial. Oh, yeah, it's real. But now when we have this, we actually have this map. And we call this map
the previous, yeah, the previous map which you constructed.
Lambda. Yeah, it's lambda.
It splits the integration map.
Well, yeah, it meets the integration map. Exactly. So we have this picture, this one. So again, as an immediate result, we have that the cohomology of M canonically split off of the cohomology of Keller differentials. So for example, the map pi, if we take a cohomology, then it's subjective not only for even degrees, but for all degrees. That just generalizes the Gomez result.
That's just one of the things you constructed, right? Because
Yeah, that's just
out of time, you have about 15 minutes.
okay.
So,
Yeah, let me kind of explain very quickly that. So let's say let's consider X a space, and F a smooth, a soft subsheaf of the sheaf of continuous functions. Now we call the global sections a soft function algebra. Function algebra. Now, a lot more complicated from the results is the following map. We actually constructed, so I constructed a map C from the cohomology of algebraic forms on the algebra of global sections for a soft subsheaf to singular
Sorry, could
cohomology.
you move your screen up for a moment?
Oh, yeah.
CX
Oh.
means just a sheaf of
Sheaf of continuous functions.
continuous functions. Okay.
so how do you integrate it? I just wonder. You cannot integrate. So I mean,
yeah. So this constructions.
case you could
this construction.
integrate, but in smooth case
Yeah.
you could integrate. But what do you do here then?
Yeah. So this construction is very, very complicated. So the idea is well, not very, very complicated, but quite complicated. So the idea first is we represent fx, this algebra, as a limit, as a colimit of finitely generated algebras, subalgebras. Finitely generated subalgebras. Then the idea is we take
Kind of finite generated piecewise, piecewise. I don't know, constant or what?
No, just it's just finitely generated subalgebra of this algebra.
But
and now, oh yeah, how do you integrate? You ask. Yeah. So this one is like this. First, we move this one to Lipschitz singular cochains on the real spectrum of this algebra. So the idea is
algebras. What are algebras AI? Because if you want to speak about Lipschitz, you need to have
any
some
commutative. Any commutative algebra is a colimit of its finitely generated subalgebras. So
how
there
do you
is
define the Lipschitz? I mean, if it's finitely generated, and how do you define Lipschitz on them and spectrum? The spectrum can be pretty wild.
So spec is a real spectrum, so just a real spectrum of AI. It's of let's say A. It's all algebra homomorphisms.
Yeah, to real line. Okay.
To R. So this space can be embedded in Rn. So this space can be embedded many different ways to Rn just by choosing the generator. Yeah. A is finitely generated. A finitely generated. Finitely generated. So we can embed the spectrum into Rn just by choosing generators. Now, the space here is an algebraic variety in Rn. So for this algebraic variety, we can define what Lipschitz simplex is. So we can define what it means for simplex to be Lipschitz.
Well, since you have metric on both sides, it's not a problem.
Yeah, we can define. We can define what Lipschitz means. Lipschitz means. And so here we can actually, yeah, and so now if you have a form, it represents a form on Rn, and this represents a form on spectrum, and we can integrate a form using Lipschitz simplices. So this one is done, so we integrate polynomial forms that come from this algebra, this DJ algebra, on Lipschitz simplices. Lipschitz simplices. Now, it's actually also not trivial. To do this, we need the geometric integration by Whitney, but but the problem is what's written in the Whitney's book is not enough, unfortunately. So we had to develop kind of a bit of theory for Whitney integration, but it works almost as written in the book. So now, but the big problem is that here are the Lipschitz cohomology, but we need singular cohomology. And here we need kind of a little bit of an unbelievable result due to Schwarze. It's 2011, if I remember correctly. Is that the algebraic sets in Rn are locally Lipschitz constructible. Lipschitz constructible.
So it actually means that locally you have kind of Poincare lemma, right?
Yeah, exactly. So I don't actually know if they are smooth constructible. That would be way too kind of miraculous, but they are locally Lipschitz constructible. So that's why, yes, you have Poincare lemma for Lipschitz Poincare lemma, and that's why you can actually then this one is isomorphic canonically to just singular cohomology of spec A.
But then you need to somehow relate the limit of spectrum.
Yeah, well, this one is actually quite simple because we have a map.
Limit, right?
Well, yeah, so we have AI embeds into fx. And so on spec, so have a map from X to spec AI. And on the cohomology, we have the map from spec AI to spec to cohomology X.
Mhm.
And that's kind of it. So again,
But
the
you
details
but
are
you don't need to go to the limit. I
no,
mean,
no, 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 no.
you have
We
not
don't.
just one map, you have lots of maps for all eyes.
Yeah, so we have a map from this one just into the cohomology of X, and then here we take limit. The cohomology and limit commute, so colimit commute, so
Cohomology, well, yeah. I mean, homology does, but I don't
yeah,
remember.
cohomology.
There is the lim1 functor which actually prevents it from being exact. I just don't remember which homology of cohomology.
No,
Is it homology?
cohomology commutes with colimits.
Okay then.
Colimits, not limits. So yeah. So the so we have this map Psi, and it satisfies the property that we expect. So an example, or just another theorem. Let's say theorem. So now let's take the space smooth manifold, and the algebra is just the algebra of smooth functions on that. Okay. So the sheaf, the soft sheaf in this case is just the sheaf of smooth functions on that. And now we have, the map from the cohomology of omega bullet C infinity M to the cohomology of M with real coefficients Psi. On the other hand, we can just go to the cohomology, the drum cohomology, using our pi map. And here just the usual isomorphism that comes from the RAM. Now we have the usual maps and our very strange map. So my claim is that this
Psi is map which you constructed in the second part of your talk, right?
yeah.
So is the map which you constructed in the first part.
Yes.
I mean, you have both for smooth and separately for everything. Okay.
Yes. And so this diagram commutes.
Not very surprising, I would say.
Yeah. So in this case, if you take just smooth forms, then this map psi is just integration. But again, this map psi works for any smooth.
It's integration cohomology.
Yes, on cohomology, yes. So this psi is not defined on complexes, on the level of complexes, but it is defined on cohomology.
So you just check it on some universal properties, right, to show that they can coincide in cohomology. How do you prove this?
So to prove it, to prove it, I actually build a map not here, but in the hypercohomology of the constant shift, and then I prove that it coincides in some sense for finitely generated subalgebras. Then check that it is functorial, and then kind of
okay. We're running out of time, but so that all the technicalities, if you went to see, you can look into your papers.
Yeah.
Okay.
So, and the last and the most important part is that now we have map lambda that goes from the x Rx to the cohomology well, let's say Cx. like this. I defined it for smooth functions, but it works exactly the same for continuous functions.
So smooth functions, yeah, you remember
Yeah, I embedded this. Yeah,
the
here
shift,
it's yeah, it's worth to work with. So for
yeah, work.
So for psi, we have a map in the other direction. So this is the integration for kind of forms with continuous coefficients, which you can still, turns out, integrate. And so the surprising part is that this composition is identical. So if we go lambda and then psi, then this one is identical. And so actually, these groups canonically split from these groups. And moreover, these maps are multiplicative. So it is actually, the splitting is actually multiplicative. Yeah. So I can talk a lot about other things, but if time runs out, yeah, then this one is
Yeah, there are
logical
lots of questions, of course. There are lots of questions, of course. Well, it looks, I mean, surprisingly familiar because you know, these questions they appear in lots of papers which deal with cyclic homology and Cauchy homology of various algebras. In that case, you can also define, well, the Kähler differentials are very popular in that field. And I've seen many times people claiming that cyclic homology, well, that they actually split from, well, the Ramko homology is prime for cyclic and so on.
Yeah, exactly. So this one was kind of the inspiration for this similarity.
I just wonder whether this has something to do with some other approaches. I mean, after all, there is something called simplicial differential forms, where you replace your space X, replace its singular complex with polynomial differential forms on singular simplices. And it's well known to give the singular cohomology, these polynomial differential forms.
Yeah.
And the proof is remarkably simple because it just is based on the properties of the simplicial algebra of differential forms.
Yep.
So I wonder whether you can actually simplify some of your proofs by resorting to this intermediate remedy of this polynomial differential forms on singular simplices. I mean,
so actually, for just a quick kind of note, that if X is a polyhedron and the functions are, for example, polynomial functions, then psi is just an isomorphism.
yeah, I
there
know.
is no lambda. Yeah, there is no lambda. The fact that the psi is an isomorphism is also very non-trivial. So this one is actually, so the fact that in this case psi is an isomorphism was long thought to be incorrect. There is a counterexample in a paper, I think in early 2000s, but the counterexample was incorrect. Yeah.
I remember it was proved in early 2000s. I mean, that if you take polyhedron, well, maybe they speak about simplicial sets rather than about polyhedrons. Maybe in the case of simplicial sets, that's simpler.
Yeah, probably. Yeah.
I remember
papers
which say that if you have a polyhedron and have considered piecewise polynomial functions and take the cyclic homology of these piecewise polynomial functions algebra, you restore the singular cohomology of your polyhedron. So I'm not saying that it's simple. I'm just saying whether it is possible to use this piecewise polynomial or piecewise smooth
Yeah.
function on simplices to somehow simplify some of your constructions, or maybe to just to relate it to something known. Because you see, sheaf constructions, sheaf theoretic constructions, they look like kind of algebraic counterpart of these simplicial constructions. So since you're still working with algebraic topology rather than algebraic geometry, it probably is advisable, if not, well, it's probably is good to use simplicial techniques rather than sheaf theoretic techniques. But I'm not insisting, just trying to guess.
Well, just a quick kind of thing. So technically, when we kind of prove some things, I use simplicial DJ algebras a lot. So for example, in the case where I prove that C or lambda are multiplicative, I extensively use kind of the simplicial DJ algebras.
So you're using some kind of Alexander Whitney and
yeah.
Okay.
And proof from rational homotopy theory that the maps are multiplicative, that the RAM map is multiplicative. Yeah. The same idea.
I mean, and what applications? I just cannot imagine. I mean, this construction is pretty non-trivial. Let's say not very natural, because it's not very natural to consider smooth differential forms of non-smooth functions. So what kind of applications you can think of?
So the general idea, if you have a space X and you want to consider the differential forms with coefficients or elements of that are not smooth, but they're almost smooth, kind of, let's say, for example, polynomial functions. So the polynomial functions, what's called a Sullivan algebra for a polyhedron, right? So here, it's not really clear how to define differential forms just from the algebra, just starting from the algebra. So Sullivan defines them.
If it's finite, why not just? If it's finite, why not just use it on the node? I mean,
like this.
You have finite. I mean, no. I mean, you have I mean, you take separately polynomial functions on every.
Yeah, on each simplex. Yeah, that's the problem.
I see.
But now we can ask, can we just take the algebra and construct the form just from this algebra? For example, if you want to feed it to a computer or something like this. So the answer is yes, you can just do this. But now the problem here, you have a map to just Sullivan algebra, DJ algebra of forms. This one is not an isomorphism, not an isomorphism.
I mean, I think the notation is a little bit off. I mean, so on the left you have lambda 0, right? On the top, on the right you have lambda.
Sorry. It's called A. Sorry. A. It's
A0 and A dot.
Yes.
A0 and A bullet. Okay.
Yes,
I see.
A0, A bullet. That's bullet. So it's not an isomorphism, but it is a quasi-isomorphism.
Yeah, it's well-known fact.
I don't think so. I think it was believed to be false.
No.
So,
well, okay, you need to check. It's been quite some time since I looked into this kind of things.
So Gomez.
I always thought it was well known.
No, Gomez in 2002 provided a counterexample that was incorrect. But Kahn and Miller in the 80s, I think, they calculated that it's not an isomorphism, and they calculated the kernel of this map.
Well, the fact that these algebras are different is more or less, if not evident, it's natural, because they're differently defined. But I believe the fact that they give the same result as cohomology shouldn't be very hard to prove. After all, the algebra on the left is finitely generated, and algebra on the right is well known to give the single cohomology.
Well, the deep problem is that here are forms that behave very, very weirdly. They have kind of almost non-existent support.
Well,
So,
yeah, but it's finite geometric algebra after all.
yeah,
I mean,
but
unless you come with some wild polyhedra.
yeah.
So I
Um,
have the impression that finite geometric algebras cannot be very wild, cannot, if not tame on the nose, they are pretty close to be tame. Okay, that's just void discussion. So I would really love to see the way you can apply it to various problems, because you see, in many situations you have to work with simplicial well, objects rather than with usual manifolds. I think in some sense, simplicial manifolds are even more natural than usual manifolds. After all, when we work with manifolds, we always work with some local parts with some local open sets on the manifolds. It's only there where we can write down a formula, right? So I would really love to see. Well, so there is a very nice book by Dupont who who actually compares such, if not such algebras, then at least some such constructions. Pretty old one, I think, from 1978. Dupont. Yeah, I'd really love to see how this is applied to various problems where global constructions are non-existent or very poorly known. For instance, if you have some, yeah, I would love to see how it works. Okay. Any other questions?
I want to ask you why you wrote in your abstract about the Grothendieck's comparison theorem. It was just an analogy.
I think
yeah, so
it was clear.
if
I thought it was clear why it was mentioned. Sorry, Alexander.
So yeah, so
no,
if
I
the
mean
algebra,
because the talk and the methods have nothing to do with algebraic geometry. So practically, it's algebraic topology.
oh no. So if A is algebra of regular functions on a smooth manifold, on smooth variety, then this map psi is a quasi-isomorphism. Kind of the map from let's say R. No, sorry, C. I guess C. To come on. V. This one is an isomorphism. But if the manifold is not smooth, if the variety is not smooth, then it's not an isomorphism. And so we can actually ask, is there a map in this sense? Well, I say yes, and but it's not an isomorphism. So kind of the idea. Yeah.
What?
Oh yeah. So if I understand. Sorry. So if the map, if the algebra is not smooth, then we can ask: is there an analogous statement for some sort of some algebras of some sort for which the Grothendieck comparison theorem is still correct? And yes, it is. Let's say, for example, A is just A0 of a polyhedron. This one is not a smooth algebra, but the Grothendieck comparison theorem still holds. So if X is a polyhedron, then the Grothendieck comparison theorem still holds, because A0 is just the algebra of regular functions on this polyhedron, but it's not smooth.
But I mean, the technique for the proof is quite different, right?
Yes. It is.
So it's that was my question, because the Grothendieck's theorem is more or less algebraic geometry. I mean, this something like okay, but you used just purely algebraic topology technique.
Yeah, kind of. Yeah, yeah. You're right.
Okay. And was a okay. So in a sense, that was just a starting question for your research, right?
It was a
starting motivation.
Oh yeah.
Motivation.
It was a motivation question.
Because from previous discussion, I thought that the motivation was given by other works from algebraic topology. Like,
well, there were a lot of different motivations. Yeah.
But it's kind of most natural analogy which exists. You have a construction which in some cases gives you nice results. And you do the same construction in more general situation, and then you hope to get something. And the talk was about how much you can get in this way. By the way, did you try to apply your methods to some non-commutative examples?
Well, the problem is in the non-commutative case, the omega bullet doesn't make it doesn't behave as good. So, and the spectrum also does not. So we can kind of try to do it for well, it depends on how you define non-commutative case.
Well, there are lots of ways to do this.
Yeah,
for instance,
So
I can think about at least two. First is take the universal non-commutative differential forms, and that will give you some kind of cohomology close related to the cyclic cohomology. And the second, actually there is a big problem in the cyclic cohomology, because if you try to apply cyclic functor to, well, some wild algebra, non-finitely generated algebra, nobody will tell you what to obtain in the end, unless you actually modify the functor by passing to topological tensor product and so on. So that is.
I think this case was done kind of by.
No, I know this. I mean, if you apply algebraic construction to non-commutative, non-finitely generated algebra, like sister algebra or something.
Just yeah.
Because
I didn't try.
Yeah, that was the question. The other idea which you can do is that instead of this universal, you consider all possible differential calculi, which you can associate with an algebra, and then you try to somehow to pass to the limit in respect to this category, or some sort of respect to some subcategory inside it. And that can be quite interesting, because even I did this exercise some time ago, and I remember that even in some very small case like finitely generated algebras, you obtain non-trivial categories. So that can be quite interesting. Okay, so it was a very interesting talk. Thank you. I really enjoyed it. I don't know about other or well.
Yeah, thank you.
I hope that they also liked it.
Yes.
It's really wonderful to know that something very natural hasn't been known for such a long time. I thought this topic has been studied extensively for decades already, so I thought everything has been known, but it seems that these construction for non-algebraic algebra, so to say, were considered a bit strange by the mainstream audience, so people just ignored these problems and these constructions, and that's a pity. Okay, thank you. And well, if you have some ideas about non-commutative algebras, I'll be happy to hear them, because you see I have some interest in new geometry. Okay. And yeah, see everybody next time. Next time will be our last seminar this year. And I think Junhu will making a talk next time, right?
I hope so.
Okay, I'm waiting for the title and abstract in any case. See you. Thank you. Thank you and goodbye.
Thank you.
Thank you. Thank you again. Yeah, bye.
Thank you.